Professor Bell, and this is going to be our video lecture in light of COVID-19. We're attempting to move as much content online as possible, so this is part of that effort. So bear with me, this presentation was not originally designed to be online, so we may hit some bumps as we go through it, and we'll deal with those as we come to it. I'm going to be supplying some additional videos in the My Courses lessons to supplement my material and supplement things I might normally work out on the board. So make sure you review those as you work through the problems and the activities in My Courses. So the exam results would normally be something we go over together in class. Since we're not going to be meeting for face-to-face class, what I'll do is I will open that exam so that you can review the content, the questions that you missed. And what we can do is, if you find something, you can either bring it to my attention through email or possibly through a face-to-face conference call type event that we'll try to have in the future. Okay, I usually talk about the cake activity that we have, and I'm going to talk about that later on when I review each of the activities in My Courses. Normally, what we would do is you would bake a cake according to some directions that I posted on My Courses, bring that in, and we would use that as an activity. Since we're not going to be meeting in class next week, we're going to kind of work through that, and I'm going to explain that later. Okay, so we've been working through a variety of different areas, and let me go ahead and get something to mark up my video with. We'll use a black pen here. We started with the product and we moved towards material properties. So now we are going to discuss the microstructure. So it's important to keep in mind as we discuss where we're heading, this relationship between the properties of a material, the structure of a material, and how that material is processed. We refer to that as the process structure properties triangle. And just for abbreviation, I'm going to put this for call this process. Forgive my terrible handwriting here, but process properties and our structure. So the idea here is that the structure of a material is dependent, the structure of a material is dependent on the processing conditions that it undergoes, which affect the properties. So all these things are related. The structure impacts the properties, the processing impacts the structure. So they're all interrelated, and as we go through this, we need to keep that in mind, especially for your product, that depending on what kind of properties you want, you're going to need a certain type of structure, which is going to mean you need a certain type of process to get that structure. So I want to talk about what is the difference between pencil lead and diamond. Normally I'd have you all discuss this and tell me what you know about this, but the reality is pencil lead and diamond are made of the exact same material, and that material is carbon. Right? It's the exact same material. The only difference is the way that material, carbon, is structured. And obviously that structure has huge implications for applications. Diamond has very different properties than pencil lead. Okay, and like I said, they're both made of carbon, but the way that the carbon is connected to itself, the way it's bonded to itself, or the way the interactions between the different atoms, that's what's impacting our properties. Okay, so how do we know what our structure is? Well, there's two types of structure we're going to talk about. We're going to talk about the microstructure and the nanostructure. So this has to do with the ranges in which the structures, the size of the geometry of the structures lies. So for microstructure, we're typically looking at structures that are over 100 nanometers large. And then for nanostructures, we're typically looking at structures that are under 100 nanometers. And depending on what size we're looking at, we may use a different piece of equipment to investigate that structure. So we could use an optical microscope, a scanning electron microscope, a transmission electron microscope, a scanning probe microscopy. All of these things are different ways that we can look at the structure of materials. So I'll let you think about these questions here. The key thing is to understand that depending on what we're looking at, the size, so if we're looking at an ant, a grain of salt, a human hair, bacteria, a virus, an atom, all these things are we can look at them with different tools. So for instance, the human eye might be able to image a grain of salt, but if we want the human eye to be able to image bacteria or viruses, it's just not possible to do that. So we have to use a tool such as light microscopy or electron microscopy to investigate the structure of those materials. There's three general categories for microstructures. There's crystalline materials, so these are highly organized, long-range patterns that we see in the arrangement of the atoms. There's polycrystalline materials, in which case we have the short-range order, but you can see how the order here in the short term is very organized, but as you get to a new position, you'll see that orientation of the order has changed. And amorphous materials do not have long-range or short-range order. Okay, so sometimes when we talk about crystal structures, a lot of students have this idea of quartz crystals or geodes and this sort of geological crystal that we're maybe familiar with, or maybe the crystals that you see people wear as necklaces. While those are crystals, aluminum has a crystalline structure too. All metals will have some form of crystal structure, and plastics can have crystal structures as well, whether amorphous, single crystal, or polycrystalline. So all of these materials have crystalline structures. So don't think that, just because we're talking about crystals, we're talking about a certain type of material. All of the materials out there can have a crystalline structure. Even if it's amorphous, that's a type of crystal structure. Okay, so I'm going to explain this activity a little bit later, but this is something you can do even though we're not going to be meeting in class. And I'm going to explain this as I go through point by point what's in the lesson later on. Okay, so let's talk a little bit about strain hardening. So strain hardening is a microstructure effect, and we're not going to look at how the structure looks quite yet or why it occurs, but I want to talk about things from the viewpoint of the stress strain curve. So here I have my stress strain curve, stress on the y-axis, strain on the x-axis. As normal, we start to put this tensile specimen in loading. We start to put stress on it, forces on it. As we do that, it's strained, and we might strain it to this point, which would be the yield strength. Starts to yield, deform. We get here, undergoing plastic deformation. And at this point, 3, what the graph is trying to show you here is at this point we take off the forces. Okay, so we take off the forces. Now what happens is, as we do that, there's going to be elastic recovery. Even though we're in the plastic region, you still undergo some elastic recovery. So you can see this line here sort of represents that elastic recovery. You notice it has the exact same slope as over here, our elastic modulus. Elastic modulus defines the slope of that elastic recovery, but it doesn't return to its original position. So you notice that right here, it does not return to its original position. This would be its original position. So what does that mean? That means it has plastically deformed. It has undergone some recovery. We call that recovery spring back in many instances. Now the interesting thing about this phenomenon, if you were to load this again and you started to go up the stress strain curve again, I'm not doing a very good job following this line, but it would follow this line exactly up this dotted line. The dotted red line is really what it's following. I'm just trying to recreate that, but it would be coming up this red line, and it would not deform plastically until 0.3. All right, so that's a really interesting phenomenon because you notice 3 is higher than 2. So what that means is my new yield strength is at 0.3. This is the effect of strain hardening. When something undergoes plastic deformation, the next time you go to apply stress on that material, you've actually raised that yield strength of the material. This is the effects of strain hardening, also called cold working or work hardening. Those are just synonyms for the term strain hardening. Okay, so why in the world does this happen? The best way I can talk or explain this is, if you imagine a really crowded street. So imagine you have a traffic jam, right? The more cars that are in that traffic jam, the harder it is for them to get through. So with strain hardening, the way that materials deform is that defects have to move through the crystal structure. Now, as more and more defects are added to the crystal structure, it actually becomes harder for those defects to move. So deformation occurs as defects move through the crystal structure, but the more defects we have, the more difficult it is for those defects to travel. The harder it is for them to travel without running into another defect and having this traffic jam type effect where it is more difficult, and by more difficult we mean it takes more energy for deformation to occur.